These are the notes for Integrated 1, 5.1.2. We're going to start talking about rebound ratios. So I took a couple still images for you guys to take a look at. And so let's say we have the person in our video that we've got shots of. And we'll see that they're holding a soccer ball. Notice also that I went through and I did some measurements for you. So based off of where her hands are located, and the height of the ball, tried to make sure that I measured from the center of the ball, that would have been 118 centimeters to where the ball actually bounced off the ground when she dropped it. Now, she's just going to release it, not throw it down on the ground, not put any pressure behind it, not pull it up in the air, just drop it. When she dropped it, the ball, and we did another measurement, hopefully getting to the center of the ball, off the ground. That gave us 70.8 centimeters. And then she just let it go. So we went through, measured to the middle of the ball, and then to the ground. That gave us 42.48 centimeters. And then so on and so forth. You can see that the height that the ball is bouncing back is getting smaller and smaller, which we expect. But that amount that it is bouncing back or not is called a rebound ratio. Ratio implying multiplication here. So what we want to do is we want to take this idea and look and see how to calculate that. Also, want to look and see what the rebound ratio is on a couple of different athletic balls. So moving on, let's take a look at, so here's the beginning of the notes. I just wanted you to see those still images before we started. Rebound ratio. So it is a ratio, which implies multiplication, like I said. So we're talking about a rebound ratio. It's how much a ball is going to bounce back from a drop height. So the drop height represents the total distance the ball travels from your hands or from the top of an object without any pressure on it. So this is the total distance, let's say down. So the drop. So the total distance down. Then on the top is going to be the total bounce back distance. So total bounce back. Now, typically, when we drop a ball, again, no pressure behind it, just drop it, let gravity do its work, it normally bounces back a fraction of the distance that it traveled. It's pretty typical. And then we'll come back to the height of the ball in just a second. So I'll come back to that formula in a minute. So what we want to do is we want to take a look at a couple situations. So let's say we have a tennis ball. All right, we are going to say that the tennis ball, and this is based off of the standards, it must rebound approximately 111 centimeters. That's how much it comes back from an initial drop of 200 centimeters. Okay, so let's write this out. So our rebound ratio, we're always going to state the total amount from the drop goes on the bottom. And then of that 200, it comes back 111. All right, let's go ahead and actually see what this is. So we're going to grab our calculator and divide. That's going to give us exactly 0.555. So basically what we're saying is that a tennis ball bounces back 55.5% of its drop height. Bounced back of the drop height. Now, the higher the ratio, the more bouncy the ball is. So let's keep that in mind. All right, let's take a look at the soccer ball. It has to rebound 120 centimeters from a drop of 200 centimeters on a steel plate. These are talking about the actual regulations. So our rebound ratio has to drop from 200 centimeters, but of those 200 centimeters, it come back 120 of those centimeters. All right, let's see what this is. 120 divided by 200, that gives us 0.6. So I'm going to go ahead and put a 0 after that so we can write it as a percent. So 60% bounced back of the drop height, or bounce back of the drop height. So at this point, just if we compare these two, the 60% for the soccer ball is larger than the 55.5% for the tennis ball. So we would say that a soccer ball has more bounce to it than a tennis ball does. All right, we've got a couple of more. Okay, basketball. Rebound approximately 53.5 when dropped from 72 inches onto a wooden floor. Okay, again, these are the requirements for this. So let's say our rebound ratio. It's going to be the total drop height. Well, in this case, the total drop height was 72 inches. Of those 72 inches, the ball has to come back up 53.5 of the inches. So let's see what this one is. Oh, wow. Okay, this one's pretty big. So this is going to be 0.743. So I would say 74.3% bounce back. All right, so out of the three that we've done so far, the basketball has the biggest bounce to it. Okay, now a squash ball. Squash is kind of like a racquetball, just so you guys know. So they're these little tiny balls with the racquetball, and they're normally pretty firm and they bounce pretty good. Squash ball has a little bit of the air deflated out of it, so it might not bounce as much. So rebound approximately 29.5 when dropped 100 inches onto a steel plate at 70 degrees. Okay, so it has to be at a specific angle, but we're not going to worry about that. We're just going to talk about how much it bounces back from the drop. So our rebound ratio, again, the total drop goes on the bottom. So where it got dropped from was 100 and how much it actually came back. We type this in, that's going to give us 0.295, which kind of makes sense because it's a ball that's been deflated a little bit and those aren't quite as bouncy. So this is 29.5%. That's how much it bounced back. So out of the four that we did, I would say the ball that has the biggest bounce to it, again, without any force behind it, is going to be the basketball. All right. So then let's talk a little bit about exponential growth, exponential decay, and then the graphs. But we are going to go take a look back at that equation too in just a second. So exponential growth, this is when it is increasing by a common multiplier. Okay, so increasing, which I think makes sense because it is growth. If this is exponential decay, it's decreasing by a common multiple. So something is shrinking. So if you take a look at these ratios that we got for the rebounds, all of those ratios, think about dropping the ball, it's never going to come back the full distance or more than that. So that would be a decay. And then the graphs of these things. Well, the graphs of these functions are curved. You and I are going to talk about the horizontal asymptote part of it later, but they are curved. And typically, they have a couple of different forms. But one of the ways they can look, so it looks like it kind of hovers right around the x-axis and then it curls up. So that's one way it could look. The other way it could look is it looks like it's kind of flipped around. So it starts really high and then comes down and curls right next to the x-axis. So those are the two you and I are going to focus on. Okay, let's take a look back. So the height of the ball, Drop height, rebound ratio, number of bounces. All right, this equation looks a lot like the stuff we did on the previous notes. So the height of the ball, I'm going to call that T of n. The drop height, let's call that the 0th. Rebound ratio, we have called B. And then we're going to let n represent the number of bounces. So we're going to be using this exponential equation, just like from the previous notes, as we move along through this chapter.